Just if you just want to describe
How many determining how many things there are determining the amount of something.
exactly the amount or how many, right? That is what this is all about. We want to learn the art. We will obviously learn some formulas on the way. We will come across formulas, but we want to understand the art of counting. Okay, given a situation, given a situation, we would want to know in how many ways that can happen without actually listing and counting. That is a major, the major the art part of this. That's why this is a area of interest. So the key here is without actually listing all. We may have to list some possibilities to see patterns and so on, but we just want to be able to somehow break the process into steps and get an answer. So can anybody maybe give an example of a counting problem that they are curious about, or that they, even if they know, if you know the answer of, or if you don't know the answer of, but something that you're curious, something that you have ever that has come to your mind, example of a counting question. So it should not be mostly from a text. It's just some counting, some question of how many that you have been curious about or thought about. Example of a counting situation, I would not even call it a problem, and you would want to know how to do it but you don't know, and so that you can keep that as your goal too. Yeah, anyone? So any situation in which you have wondered how many, I wish I knew it directly.
So there was some sums where it was a big number, and how many times can we write this number without, if you can repeat any digit. And
Okay.
then we got 25 times.
Okay, okay. That's a very standard example, but that's nice. That's something, yeah. But something, anyone who, that just came to your mind while studying something, or you've just thought about, not from a book maybe, but just something that you want to know. Anyone in some real life situation maybe, like maybe you have your classroom and you have friends and there are some allotments or some team. If you ever wondered about how many ways could this be done, I wish I knew a fast way to do it. Anyone? I'm sure you would have thought, all of you would have thought about maybe it's not coming directly in your head. So, but still, yeah. So there are some very natural questions, and that's why this is a very, it's just a natural set of questions. And I'll just give some examples, and you'll see natural questions. Obviously, digits are there and so on, jumbling up digits and so on. But there are some natural questions, okay? So, suppose from a set of 20 candidates or 20 players, suppose in your class you have 20 people, but we need to select only five, unfortunately, for let's say some kind of an exam, some quiz or some event. From a set of 20 candidates, select or make a team of five, right? Now, you may or may not have thought about this. Both ways is fine. The question is how many ways to do this? Yeah. I'm not writing that, but that's a question. How many ways can this be done? And the real interesting part is that this can be answered without actually listing all the possibilities. 20 candidates, you can list your 20 friends' names and you can keep choo- uh, choosing five. There is so many ways to do it, it will not end. It will take a long time. But there is a fast way to do this. Anybody has any sense of how this could be approached? Just If you just put this question right now, we're not going to answer this today, maybe, but just in case anyone has thought, how would you know? So basically, I should complete the question. How many ways to do this? Just how many, not what are all the ways. So we will answer this question not today, maybe, but after some time. This is little interesting. Meanwhile, you guys can think about this. Okay, you guys can think about this. Maybe you can reduce this number from 5 to 2 and think. Okay. In any ways, so I will be basically will be developing the techniques to answer this kind of question. And yeah, so let's get started with examples that maybe we can do, okay, with a little bit of help, and that's how we'll progress. And since someone referred to digits and such, maybe that's the thing that we are most comfortable with. So let's see some examples of counting questions. Counting. 1 minute, someone is joining. Counting problems in the context of digits and numbers, because I think this is a topic, this numbers we have been using, so in the context of numbers and digits. Yeah. So this will be fairly standard. Just today we'll just do some standard stuff, and then we'll see how comfortable people are, and then we can raise the bar and so on next time. Okay. So let's start with a question. It's a very simple question. How many? Just you can put it elegantly. So how many three-digit odd numbers? Maybe it's just some people may even be a silly question, but let's answer this. Let's start with simple stuff and see the methods here. Yeah. So how many three-digit odd numbers are there? Uh-huh. Right. So you're using symmetry. That's a interesting way. Right. So let me break it down into steps though. So people have already said, and it will work out. Step one, find all. So I'll just write in a way that you can relate to it even later on when you're in other complicated situations. This is simple, obviously. Find all three digits. Find all. And step two, use symmetry. Yeah. What do I mean by symmetry here? Would anybody want to say what they understand from this? Use symmetry. There is a symmetry between odd numbers and even numbers, right? For every odd number, for every odd number, and for every odd number, there is an even partner. Just very roughly speaking, right? Just take an odd number, 101, there is a partner 100, if you would like to think like that. Okay. Yeah, this is, or 1 minute. Yeah, roughly that is, so roughly that is correct. Yeah. For every odd number, there is an even partner. So just take the number before it, something like that, right? So in this way, you will roughly get the right answer. So what do I mean by here again use symmetry? I mean that because for every odd number there is an even number, so there will be half of them will be odd and half of them will be even. So you divide the answer by 2. Okay, so that is very simple. Can we exit and let's see if this is correct. Okay, should be correct, sounds correct. So can anybody fill in the details, because we want the answer, right? We need to know the number, we need to know the answer at least. So details will be how many 3-digit numbers are there. That's step 1. So how many 3-digit numbers are there? Just we can quickly say that.
900.
Only 900 or okay, 900. Yeah, that's correct. 900. 900 is correct, right? And so you're done, right? If 900 are numbers are there, obviously half of them are even and half of them should be odd. Okay, is that correct? Or yeah, yeah, you can just take like this. So if you have
Yeah, that is absolutely correct.
why?
Because from 1 to 9, if we take, there are 5 odd and 3 even.
Nice. That's a good catch. That's what I'm saying. So we have to really be very very careful here. That is the point. But in this case, there is no problem because so that's a very good catch. That's what I was trying to hint at. That if you take the numbers from 1 to 9, let's list. I mean, yeah, if you take the numbers from 1 to 9, there are 5 odds and 4 evens. So there is an imbalance. But in this case, there is a balance, right? Because from 100 you start and you end at 999. So you're starting with even and ending with odd. So there will be a balance. So that you can check. You can take some other example which starts with even and ends with odd, and you can check there is a balance. So there is a balance, and you can divide by 2, right? So it should be 450.
Alright, so 0 to 9 is also if we track closely.
Yes. Then it's right, yeah. So you have to always be balanced in the sense that if you start with an even, then you should end with an odd, and so on. So the moral of the story is that it's very easy to get confused with these things. Just take small examples and check. Okay? Take small examples relevant to your thing. That is, here it's starting with even and ending with odd, and also the answer is even. Total number is even, so it should be half half. All that you can do. So here we have used the idea of symmetry. This will be crucial. In some cases, this will be the only way. Okay. Let me not give problems related to that now. We'll do it just after we have few more techniques. Just okay. But is there an alternative, more standard way, which is also a very powerful method? We should always know to do this in many ways as possible. So this is the symmetry, or this is later we will generalize this to what is known as the bijection principle. But in any case, for now, let's not throw in the words symmetry. What should be an alternative way? Which is really, this alternative way is really at the heart of multiplicative counting. Anyone? What should be a different way? Especially if those who have not yet spoken. Anything, see, don't be, it can be wrong, what you say can be wrong, right? Doesn't matter. You can just, if you've thought about it, just say. What can be another way to do this problem? Okay. Let's think about it. Let's break the problem down into digits. Okay. So maybe I can say that break into digits. See, this is really redundant in this situation, but we should know how to do it in different ways, because sometimes one of the ways only will be useful in the other problem. So we should know the different ways. So just break into digits. Okay. Also, please interrupt me if something is not clear, because Uh, some of you are joining for the first time, so you should interrupt me because I do not know where you're standing. So, break into digits. So, we have three digits. We will be focusing on one place at a time. Okay. Look at, you may think I'm going into so many details, but this is the heart of the what we will later see, the multiplication rule. Okay. So, it's good to just see it in details. Look at one digit at a time. So look at, basically I'm saying, look at it, look at this problem from the perspective of the places. There are three places. Look at it from the perspective of the places. I'm using the word perspective here. This again is, it's a good phrase. I mean, if you think in terms of phrases, then rather formulas and so on. Right? Maybe. Okay, one digit at a time, one place at a time, and see how many options you have. How many options? Yeah, so can anybody try to finish this from here? Just
It's like 1 1 and then odd numbers after that. Like 1 3 4 7 and continue from there.
uh, it okay. That's a different way. That's another way. That's a third way. Okay, but so yeah. So what I think Shana was saying this, yes, but you want to really know how many options are there for each place, right? And so basically, if I just ask a more concrete question, if I look at the units place, then how many options for the units place? Again, I'm just doing this in very details, but just bear with me for now. How many options are there for the units? Just forget about the problem and just, or I'm saying that just forget about the other places and just, uh, be the units place and ask how many options do you have?
5.
Absolutely, right. That's right. So you have five options, and let me just make it very, so we have first, it's not a first step, I will say. First step is the units place, and we have five options. Now I'm drawing all these things because if some of you may have heard, there is this multiplication principle, but students keep getting confused, and not students, all of us, I get confused about whether you should multiply or whether you should add or whether you should not multiply and so on. That's why we want to very clearly understand why we that do that multiplication 5 into whatever will come in, right? So here is the thing, let's think about this. We have 1, 3, 5, 7, and 9. So this time I'm actually um, just writing it out. Now, how many options are there for the tens place?
9. 9.
Nice, right? So units place again. Let's bear with me. Units place we have five options, or I should use the most standard word, which is choices. Okay. The idea is to get very clear about why we multiply. Okay. That's why five choices. And for the tens place, we have nine choices. Is this right? Do we have nine choices, or would anybody want to correct if this is wrong? Do we have nine choices, or
Correct.
okay? Why not 10 choices? Why can't?
Put 10 as a digit.
No, but you can put zero.
If 10 choices can be there.
That's right. That's right. You can put a zero, right? So there are 10 choices. Yeah, one has to be careful about it. But these are just small nuances, which is just a matter of focus. So that's not very anything problematic. So there are 10 choices, but there's something more is happening here. Let's even make this question more simpler, and let's just take two-digit numbers. Just want to explain a very important point. Now, you guys obviously know the answer to this already, but still, just see the method. Here is what is happening. For the units place, we have five choices. Very good. For the tens place, you have 10 choices. Very good. But there is more to it, right? Because I'm sure you guys would feel that now the answer, just for the two-digit case, answer should be, or if I just say this, let's say 10 into 5. Why do you think this is correct? Why did not I add? If I just tell you this is the rule, suppose the teacher tells you, suppose someone is in a rush. In a rush, I'll just say this, multiply, just multiply them. Why did I multiply? Why not added? So that's my question, right? Why? Yeah, why not add? Why is the answer not 15?
Because for each of the 10 choices, for one choice, there are five choices of units.
That's exactly the point. That's right. So it's more than just units place has five choices and tens place have 10 choices. Okay, tens place have 10 choices is a coincidence, obviously. But yeah, right. So the point here is that what we call, we use the word, so this word can be slightly confusing or sometimes, but we use the word independent here. Okay. This word I don't like to use while reasoning, but this word is what you'll find in books and also on. Sometimes you can use it as an escape when you're writing a solution also. What do you mean by independent? Independent means that the choices that are made in the units place do not really depend on the choices that are made in the tens place, right? That's sort of what it is. But really, the right phrase is what someone has already said, is that for each choice, okay, for each of these five choices, there are 10 choices. So let me make what is also known as a tree. We have been doing graph theory in the other class, so those guys would know it formally, but still, informally also, this is it. What is, you can feel it like a tree, it's branching out. Obviously, I can't draw all the 10, but you can understand. If I take a bigger picture, you can draw. So there are 10 choices, and then for this also there are 10, uh, 10, and like this. You see, for each of these are not 10, but 10, 10, 10. Okay. For each of the five choices, there are 10 choices. For each of the five choices, there are 10 choices. Okay. So imagine that you were in a world where there was only addition. Then this would not be useful. Okay. So historically, I mostly I believe this because it's hard to really trace the actual reality. But historically, if you think of, if you if you only live in an addition world, so this is just slightly philosophical point, but just think about this. If you live in an addition world where the concept of multiplication does not exist, for a second, just think that the concept of multiplication does not exist, then will this be useful? No, right? You see, addition and multiplication came later, right? These kind of situations were there all the time. Not in the form of digits, but from one place to the other, there are three ways to go, cross the lake, and then maybe four more ways to cross some other problem, and then finally reach home. So we said, okay, three choices here, and then for each of these three, there are four choices there. But if you live in an addition world, then it's not very useful, right? In an addition world, the answer would be 5 plus 5 plus 5 plus 5, 10 times. Okay, so you see, these kind of situations kept coming up all the times. So there, a lot of times, addition was like adding the same number again and again. A lot of the times, in the historic sense, addition was more like adding the same number again and again. Okay, the numbers didn't really change. You know, sometimes they change, but it's mostly constant. That's why We introduced a symbol. So this is just the game of symbols. um, Maybe this is a slightly underwhelming point, but it's just the symbol, right? We introduced a symbol to condense it. It is nothing profound in that sense, but in some sense it is, because it somehow we also know how to multiply this. So we made our number system also in a way that we know the answer is 50. That is the magic. The game of symbols is all a game of symbols if you think about it. Okay, so in some sense multiplication, was the successor of the multiplication rule. So what we have discussed is the multiplication rule, that you should multiply, because if you come back to the ordinary way in which we have learned things, right? If you know what multiplication is, then obviously for each of the choices, each of the five choices, there are 10 choices. Okay, so 10 is coming five times, and so I should multiply. Very nice, easy. Done. Answer is 10 into 5. And you have understood the concept, you can apply it. But this might make you think that, yeah, multiplication was a very useful tool that I used here. No, the way I think about this, and historically, otherwise, why would you need multiplication? Why would you want a new symbol? Why would multiplication be useful? Multiplication comes later, right? This principle comes first, that the same thing is coming again and again, right? So I want to just use a symbol, and that symbol is for this meaning only, just to condense this. And obviously, it's remarkable that we then know how to multiply it also. We have made our number system in a way that this multiplication, that's a deep thing, that if you think about it, how miraculously, right, it happens. It's really a interesting thing. Same things happen in very area and integration and so on later on, and many other places. Okay, so really the idea is that the multiplication principle, which is what we have already seen, I'm not formally stating it. If you want, I can state it. First step, you have some A choices. Second step, you have B choices. And if for every choice there, for each of the A choices, you have B choices, then it's A times B. Simple. That's what you've already understood. But multiplication principle comes, and then we use the symbol of multiplication comes later. Just a symbol, and this is actually the conceptual part. But we usually see it in the other way. Okay, because maybe formally the multiplication principle was came later. That's why the word multiplication is there in it. But actually, the concept was already there, that preceded it. Okay, so I'll not go more into that. Come back to problems. But are there any questions? Okay, about just the method we'd used to do this, the multiplication, simple thing. Any questions? Okay, so maybe I'll just go.
Sir, why is that units one only independent principle? We can also use that for units as well if they are side by side.
That would be perfect. There would be no problem in that. That would be the perfect thing, and you would obviously get the same answer. So independent here means that if I made a particular choice, suppose I chose 1 as the units place, then for this number 1 I would have 10 choices in the tens place. If I chose some other, then it doesn't matter, I would still have 10. So what I'm getting in the tens place, how many choices I'm having in the tens place, does not depend, is independent of what choice I make in the units place. That's the way in which we are using the word independent. Okay, but as I said, the word is not very even misleading sometimes, but we use it all the times, because a lot of times in the context of probabilities, we want to just sneak away by using the word independence and not proving it, because it gets clumsy to prove, because that by that time we are mature people, so we agree. Okay, okay, so this is simple matter. Another key aspect was that for each choice here, there was same number of choices in the other way. Okay, and obviously this could have been done the other way. You could have first looked at the tens digit also and done it. But usually our instinct is, we want to see that if some place has a constraint, we want to first deal with that first. Okay, you can. That's the instinct. But yeah, anyways. So there are no questions. We'll move on. Okay. I will just do a formality. I've just a formal example though I guess most of you have understood this already. And just to show you a situation in which we do not multiply. It's a very simple thing, but still. Suppose you have this house, your house, and suppose there are three gates on this side, and there are two exits. Huge hall, let's say. Okay, three doors on this side and two doors on this side, and let's say you are in the middle. You're inside. Now, let's say that a fire breaks out. Just example, obviously. So a fire breaks out, and you want to escape. So how many ways are there to escape? How many ways to escape? Yeah, silly. It's a very silly question, but you see, we don't multiply two into three, like obviously, right? Because just if I just want to bring the word independent here, and I use the word dependent here to do my explanation? Yes. Here, the choice I make on this side is dependent on the choice I make this side. If I choose any of these three, then I cannot choose that. So there is a dependency. Okay, so this is probably getting too formal and boring, but yeah, that's just an example. Anyways, let's move to some interesting problems. Okay, so I will not do the common ritual of just doing other examples with other types, simple variations. I will give them for homework, and you guys can try it, simple ones obviously, and then we'll pick up the harder ones later on. Let me do one hard, slightly more interesting question now. Okay, and this will be also interesting for those who have done number based and so on. But anyways, let's think about this. Suppose I have the numbers 6 cubed, 6 square, 6 to the power 10. I have these three numbers, okay, with three copies of each. Okay, so basically I have this. So I have these nine numbers. By addition, the question is that by addition of some or all of them, how many different numbers can I create? This is a slightly fun question. How many different numbers can be created? Let's think about this. So by addition of some of them, I mean that you can just let's take some examples. Anybody who would want to come forward and give some, just I don't want the answer. Someone knows the answer is very good, but just want examples. Can you give some examples so that the question becomes clear for all of us? That's right. I can do 6 square plus 6 square. I can do 6 square plus 6 cube plus 6 to the power 10 plus 6 to the power 10. So I can use any number of comments. I can use at most three copies, and I may not use also. So like these, okay. So I suppose the question is clear. The answer, I'm not expecting it to be very simple, but and the answer is simple, but the method may be not very simple. But in any case, let's think about this. So this was some context question. Anyways, yeah. This will also motivate us to learn some interesting number theory later on. So there's a bit play between them. But in any case, let's do this first. So you can, yeah, anyone, you can use no copies, you can use one copy, you can use two copies, you can use three copies. So here we have to really break it down. We have to focus on how do we break the problem. So basically, you should think of it like how many ways are there to use the six cube. No? So I'll just use slightly different language here just to make it a prototypical, and this is also very prototypical example. Means just like a skeleton of the exam of how a particular number would look like. Sometimes this can be very useful. Okay, form I should say. How would your final number look like in the most general form? It would be something like this, right? Some copies of 6 square, you could use 0 copies also. Is that right? Some copies of 6 cube could use 0 copies again. 1 copy, 2 copy, 3 copy. And some, you see, now the problem becomes, looks more tractable, right? Is this okay with everyone? This, what I have written here, prototypical example. Like it's just an imagination, right? Okay, if I make a number like, just look at these numbers. Okay, this is 2 times 6 square, this is 1 times 6 square, 1 times 6 cube, and 2 times 6 to the 10. Okay, very nice. So every time every number is like this only, right? Now what do we need? Now how many choices are there for for what? Let's think about that. So what all can we fill? Let's again, just like the case of digits, what can we put here in this yellow box? How many choices are there for the yellow box? Anyone? So I, there are four choices, right? I may not use it, so I can put a zero there, or I could have put a one, two, or three. Isn't that right? Simple. Just four choices. Yeah. So there are four choices. Obviously, I have to use one of them every time, but I can change them and make many, many ways. So I have four choices. Is it okay with everyone? Yeah, just very simple. Just writing the answer in the form. Okay, let's imagine how it would look like. Just changes the game. Okay. Obviously, all this would look very trivial when you look back at it after some time, maybe, hopefully. Yeah, well, it will. And then here, also, you have four choices. You see how simple it becomes? Obviously, there is a catch here, but it looks. Oh, no, it's not. I'm sorry. It's 6 to the power 10. Just to go. Yeah, sorry. So that's, yeah. Okay. So what should the answer be? Okay, can you give an example?
like 6 square into 6 cube and then again 6 square into 6 cube. It can't be different.
No, no, but you're not multiplying, right? You're adding them. No, no, you're adding them, right? I'm not, yeah, yeah, you're adding them. Otherwise, yeah, what you're saying is correct. If you had to multiply, then that's right. 6 square into 6 square and 6 cube into 6 cube, this would give 6 to the power 10. So you can get it in two different ways. But here we are just adding. So it's very, the cautiousness that you practicing is very, very good. That's a very good thing, I would say. But Let's say you just had 1 second if you had to answer this question. Just saying, huh? Then the first guess is 64. Yeah, 4 into 4 should be the answer. Well, I'm not saying we have proved it, but yeah, this is the first on the first look. That's what it seems. Is that okay with everyone? If we just blindly apply, if I just blindly apply the multiplication principle, then this is what I will get. Okay. So obviously there is a catch which already has been said. If there are no, I'll just use the word common numbers. If there are no common numbers, so how do we ensure that there are no common numbers, or are there any common numbers? Let me just expand on that word common. So the only fear that we have here is that it may happen that two different ways may give you the same number. That is really what the thing is, okay? Two different, so I'm saying may give, I'm not claiming either way, okay? Two different numbers or two different ways, a selection of weights or whatever, two different weights or just ways may give the same number. This is the fear that something, maybe some number 50, maybe something like, we can just take an example. Let's say 6 square plus 6 square plus 6 cube. How much will that be? I don't know. How much is 6 square plus 6 cube? 36, 252. Right. So if you do 6 square and 6 cube, you get 252. We may we may have a problem if you can write 252 in a different way. Right? Can we do it? Can we write 252 in a different way? I mean, of course, using these weights which are available to us. Another way? Is there another way to do it? Just a question. What do you guys think? What do you guys feel? Should it be possible? These are huge weights, mind you. Compared to the number of copies you have. Hmm. Right, right. Because you see, and is that clear to everyone, right? You can just try out. Right? You can just try out the possibilities. Okay, let me use 6 cube and 6 cube. That already exceeds. Then let me use 6 square several times. If I use 6 square several times, then I cannot reach to 52. So it seems ancestral pattern is big. So answer is no. No. Uh-huh. Right. And the claim is that no numbers will overlap. That's the claim. Okay. You guys should try to think about it. It's not a trivial question, but think about it. Okay. Claim is no common numbers, no overlaps. Okay. I'm not making this formal and such, but just think about it a bit. We'll discuss it later. But for now, you at least know the answer because of the principle. Now, should think or just take more examples and try out and try to get a feel. Ki why is it that I am able to write one number in only one way? Can a number, if I can write it, I can write it in only one way. There are no. Okay. So first question is to all of you. You guys got the method, the multiplication principle, as it's called, so called. Okay. That's number one. And number two, you guys understand the the mathematical obstruction, the mathematical rigor that's lacking. Okay. That is, we need to show that there are no common numbers. Okay, so we need to at least understand that there's something is missing, and we have explored it concretely. Think about it. We'll try to prove this next time that in fact there are no common numbers. Okay, the idea behind this, the real idea behind why there are no common numbers, in some sense, is that look, these are very big weights compared to the number of copies, right? So each weight is creating a huge impact. Okay, and there are small number of copies, so the impact of some particular weight cannot be like made up by the other weights because you don't have too many copies. Is that intuitively makes sense to anyone? Because it's just a rough, very very rough. Yeah, intuitively, okay, that the impact of one weight cannot be made up. So something like, the impact, just an intuition. And if you ask some old age people, people in the past, um, who used to use this weighing, this very interesting thing which I was just thinking, so I was trying to explain this to someone who doesn't do maths at all. Okay, but they kind of they kind of knew, yeah, weights, right? Then they would know that no, if the numbers are big, then you can't really measure one object. Let's say you have some bag of rice or whatever, some big bag, 50 kg rice. You can't measure it in many ways, on this, if you're not using the same, if you're not using too many copies of the same weight, right? And so basically my point is that the impact of 6 square, right, is impact of 6 square, or impact of 6 cube rather. The impact of 6 cube, the movement that 6 cube creates on the number system, right, on the, okay, cannot be made by 6 square, by 3 copies of 6 square, even by 5 copies of 6 square. Just think about it, right? 5 copies of 6 square are still less than 6 cube. That's why. But if I give you many more copies, then there is a problem, right? Okay, if there are many copies, then there is a problem. But since we only have 3 copies, there will be unique. We will try to prove this is more like combinatorics, or can also be done number theoretically. But we are now doing enumerative counting type combinatorics. So meanwhile, you guys can think about it. And you guys would have experienced this when you're buying fruits in the market. The fruit seller or the fruit seller, what he'll try to do, he has some fruit on this side. Sometime, I'm not saying they always do, but if they are using that old method, right, they'll try to put many small weights, right? They'll try to put many small weights and weigh your thing, so what that does is, they kind of benefit from it, if you think about it, right? Or rather, no, I think, no, not like that. When you're buying something, actually, I had a shop like this where you used to buy things. So I'm not saying we did, but anyways, yeah, when you're buying something, right, you would like to use many copies of the same weight. Okay, and because you can do that, the non-uniqueness, and so you will benefit from it, because you get some errors. Just, you can think about it. Yeah, but then chances of error increases, right? Because if each of your weight is, each of your piece of your each small weight, if you use many copies of it, then they will gather some dust or some coating on it, right? So you're actually able to buy more by, paying them less, if you're the buyer, buying some scrap or something like that, right? You'll win. And so the person who's selling you will say, no, no, just use that big weight. Why are you keeping so many small copies of, so many copies of small weights? That is usually considered a bad practice. Used to be. Maybe you guys can't relate to it too much, because that this is from 80s 90s time. Our grandfathers used to tell us these things. In any case, now we have a digital system. Anyway, so this was a this really relates. This idea is it goes a long way. These ideas go a very long way. They are used in higher maths. So okay. In any ways, we'll discuss this. So this was an interesting question. Let's keep rolling. Let's keep rolling. We are going very slow today. But I think it's fine. First class. The next problem I want to do, this is in fact, I'll tell you this because it's relevant for us. It is a 2018 PRMO. I thought we should do a question like this also, PRMO question, and I think this is problem number three. Okay, so this has the flavor of counting and digits. Okay, it uses some numbers, some number theory, little bit. I'll check. Interrupt me if you don't understand. Yeah, counting in digits. Okay, this will be slightly harder because this is a PRMO question. Let's see. Okay. We are looking for this. How many six-digit? Okay, how many six-digit numbers, palindromic numbers? Okay, of the form. So just write the form of the form a. Forgot the question. I know the question, but I just want to keep the same symbols because it's on now, so I don't have the question. Anyways, let's just change the symbols. Then. So symbols will be slightly different, but the question will be the same, of course. Okay, how many six-digit numbers of the form this type? So you can understand, right? This is like 2, 3, 5, 5, 3, 2. So this is palindromic. Yeah, basically this is a palindrome. This is what is known as a palindrome, right? In any case, that's the word not important. How many numbers of this form, six-digit numbers, are divisible? So this is a divisibility twist in this. Divisible by 3. So I'm just doing these questions a little bit now. Some classes we will not do any questions like this. We'll just do methods, but let's just see this. Try to understand how to do this. Sorry, not 3. 3 would be 3 is also a good question. Right? How many divided by 3? No, but let's just stick to the question. 3 would be easier. Divisible by 7. Hmm. Let's think about how to do this. So try to very first, maybe if you would like to do that, construct an example. Can anyone construct an example of a number like this which is divisible by 7? It's not necessary to do for it. It's not necessary to do that. So maybe if you read the official solution, maybe they won't do the example. They just do the method. I don't know. But we want to just discuss the question, not just do it. So the number guys, those who would like to play with numbers a lot, that's not the only way to measure mathematics. But some people are more inclined towards numbers. They may be able to construct example quickly. The number geeks. Can you think of a? You can just take some simple numbers, right? You can just try 1 0 something something 0 1 and see what you can fill there and make it work. Owie, 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 owie. Yeah, and they had another condition which is not really doesn't really do anything. It's just a useless condition. So let me not say it. I'll say it in the end. This is much more elegant. So let's try to make an example now. So let's try the easiest thing. Right? 10 cc. So I don't know what cc should be, but let's try. Just this is the simplest way, right? This is the simplest way to get started. Now, what would you fill in place of c to make this divisible by 7? Oh, 5 works. Okay, let's see. Aha. Yes, this works. That's a good guess. How did you guess 5? Okay, so you use some trick. That's good. Yeah, so 5 works, right? I let me just check it also. I just check it for myself. Um, yeah. So we have 3, 5. It's not divisible, right? Yeah, it seems like it's not divisible because 2 and 4, 5. No, 51 is not divisible. No, no, it's not. Doesn't work. 5 doesn't work, but that's okay. We have one less case to deal with. So if 5 doesn't work, then what should we take? Let's just check what works. 5 doesn't work. Does 6 work? Does 7 work? You guys should quickly just check, right? What C works? If you take 1 and 0, so we have, yeah, 8. Does 8 work? Is it divisible by 7? Yeah, right. I guessed it because of some other thing, but 8 works, right? C equal to 8 works. Now you guys can think if there is some other way, some other C that works or not. Okay. And the idea is that there will not be too many C's that will work. If you if we fix the A and the B, if we fix A and B, then um, then there will not be too many choices for the C. That is sort of what the idea is. Okay. But you see, with this way, how will you do the question? This will take a long time. You have to do a lot of casework. Okay. So yeah, you have to do a lot of casework. So really, we will not be able to do the problem like this. We will have to use a representation of numbers. Okay, let's try to understand that. That's the method. So what we are really trying to understand is, see, if you have something like this, okay, and you want to understand if it is divisible by 7 or not, right? What conditions would you put on these things so that it's divisible by 7? First thing is the following. If you take a number, you can just take 2, 3, 5, 9, 2, 1, something like just any number. You see, you can write this number in a certain way. So, for example, obviously, all of you know that let's say if I take the number 95, this 9 into 10 plus 5, right? If I take 951, then it is, this just means that you have uh, 9 copies of 10 square, this and this. Is everybody familiar with these things? Okay, this is okay. So this is just the way you write numbers, but this is a very powerful thing. Okay, obviously later on the language of modular arithmetic, when it's done, and I think it's good to just see things like this. Then you can understand later that modular arithmetic is just a language to condense these ideas, but the ideas should come first, I think. So along these same lines, you can do something more interesting. Something like, you could also write 95 times 10 plus 1. This is also correct. So in the same way, what I will do is I will write this as 235 times 10 cubed plus 921. Okay, and this is correct, right? This is just can be written because that's what this is. You can just understand. So this also I will be breaking it. I will be breaking it like this: 10 cubed times ABC. You can look at it. You can think about how why I broke. So first of all, you guys may not think about doing that because maybe I've not done a question like this. But you will see this will be the general principle in questions like this. Okay, you have to break the question, you have to break this thing into its more fundamental meaning, I would just say. Because you see, this is just a representation system. Just to mean that you have used 10 cube copies, sorry, a copies of 10 to the power 6, b copies of 10 to the power 5, and you've got this number. I don't, maybe you guys are not, some, not all of you would have done number systems like that. But in any case, that's a very interesting way to look at things. But at least you would agree that this is correct. Okay. On the grounds of symmetry, this makes sense to do. Yeah, palindrome, so you want to split it in between. But another interesting thing is that when you divide 10 cube by 7, right? When you divide 10 cube by 7, the remainder that you get is 6. Let's just divide it and check. Obviously, later on we will see some good techniques for that. But 10 cube, that is, if we divide this by 7, let's just see what we get as a remainder. Okay, 2, 7, 6. You see, you get 6 as the remainder. 6 is very interesting number because you see, I can just let go of some traditions, and I can write like this. Same thing, just chipped 1 7 in and just minus 1. Okay, so I will say that as long as I'm interested in dividing by 7, I can say that 10 cube is like a minus 1. Hmm? If I want to understand if this is divisible by 7, then basically, if you want me to do the steps, I will do it. So that's what it is. It's this minus 1 times ABC plus CBA. Looks very artificial, right? But the rule of the thumb is that 10 cube is minus 1 when you're interested in divisibility by 7. Okay, by 7, not all surface. So you see, if you want to know if this huge thing is divisible by 7 or not, it's enough to just be looking at this portion. We can forget about this. Is it okay? We can forget about this. So this is probably a new things, but right. So that's what we are doing. So this just boils down to this: is this thing divisible by 7? How many ways are there to, to answer this question? How many A, B, and C's are there so that this is divisible by 7? Okay. We will further break it down. We will further break it down as follows. We will use the definitions of these numbers. What is this? This is 10 square times. That's right. That's right. So this is just minus 100A minus 10B minus C plus 100C. So I'm just writing it down very clearly. You will see that the ideas are very simple, but there are just one idea on top of the other. But this very clumsy notations have come up. That's why we need modular arithmetic soon to just condense these computations, and also a way introduce notations so that we can do these calculations just like we do addition. And so that's what modular arithmetic is about. We will see that later, but for the time being, these questions, these are all same. These, we have not done anything. These are all same. Okay. So now what is it? You see it reduces. So what does it reduce to? You get minus 99. You see the b goes away. The b doesn't, so this says that it doesn't matter what you put in place of b. It's a shocking thing, but that's true. Maybe it's shocking, maybe it's not shocking, depends on what your intuition is. But you see, that's what truth is, right? That the b doesn't really matter. It just cancels out. So the question has boiled down to this. Anyone is not comfortable with this, please say. I'll just repeat this or say it in a different way. Okay. So now we are down to this. Now how can we simplify this further? So the question is down to this. Okay, that this number is divisible by 7 if and only if this is divisible by 7. So the b, so you know that you can put anything in place of b. So there are already you guys know there are 10 choices for b. Okay, that you can already write. But how can we further simplify this? Can we further simplify this? That is the challenge in front of us. Right? How to further simplify this? Can we? What about the 99? Can we do something with that? We can divide it by 7. That's one thing that you can do. But also, you can do a little more than that. That is, yeah, you can divide by 7 and then you will see that it will simplify. But also, in one step C, you want to, this question is 7 dividing this quantity? But 7 has nothing to do with 99. 7 and 99 are orthogonal worlds. Means 7 and 99 are completely, they don't know each other, right? They have nothing to do with each other, right? So this is the same as 7 dividing C minus A. 7 and 99, just to say it in the right words, 7 and 99 don't share any factors. They don't share any factors, right? So 7 divides this quantity if and only if 7 divides. The only hope is that 7 divides C minus A. So 7 divides C minus. This comes down to just this. Just this. Okay. Um, so basically, we need to see how many ways are there for this to happen. 7 to divide C minus A. And remember, C and A are just, obviously, you guys know, maybe. So, what are the options for A? Total options for A? No, yes, the number. Okay, so let's start with that. So, if A is 2, then what can C be? Perfect. Is everybody agrees with that, right? We want just 7 to divide C minus A. We want 7 to divide C minus A. So if A is 2, C can be 9. Can C be anything else? Is there any other possibility? 9 is certainly a possibility, I agree. No, 8 minus 2 is not divisible by 7.
8 minus 1.
No, no, if A is 2, so let's focus on the, if A is 2, then what are the possibilities of C?
Another possibility.
Okay, let's think about that. If A is 2, then what can C be? Who thinks that there are more?
5.
No, C has to be a digit, right? You must not forget the roots of C. What are the other ways? What is there any other possibility for 7? Sorry, for C. Anyone? So C is just a digit, okay? But what should we put here so that 7 divides C minus A, right? So that 7 divides. This works because 9 minus 2 is 7. So A is 2. What else can you put in place of C? Come on, there is one more thing. There is one more thing that you can put. Mm, what else can we put?
Can C be 2?
That's right. C can be 2. Why not? Yeah. C is 2. Then it's the simplest way. In fact, I would think of 2 first. Maybe I'll forget the 9. Okay. But in any case, you see there are two choices. Okay. If A is 2, then C has two choices. Let's not forget A equal to 1. So if A is 1, then what can C be? So again, C can be 1 or 8. Hmm? Then similarly, you have to keep doing this. If A is 3, then if A is 3, then what can C be? Again, our goal is that 7 should divide C minus A.
7 to C minus A.
Yes, right. So in this way, you can get all the possibilities, right? And see, now you don't have any other possibility. You because other possibility is 10, but 10 is not allowed. 10 is not allowed because C is a digit. So in this way, you can understand, right? It's very simple. It's 4, then C is 4. It's 5, then C is 5. Mm, is this correct? If it's 6, then what can it be? 6. Anything else? No. If A is 7, then what can 6 be? C be
7.
7. Okay. So let's keep moving like this. We have to do some listings. Okay. Maybe as you get more mature, you won't have to list all of this, of course, but for the time being, let's do it. C is 8, then C is
Possible.
not possible. Let's think about it.
Yes, C can be 8.
Okay. Anything else? Especially someone who has not yet said in the yeah. If you want to imagine what can it be, 8 is definitely correct. 8 minus 8 is 0. What else do you want to put? So you want 7 to divide C minus A. Right? You can put C equal to 1, right? Because see 1 minus 8 is good, right? So this is easy, but it will just be open to all the possibilities, and you will get all the right answers. Okay, so that's good, right? Then it's 9. Oh, this is a big list. Then it is 9 and 2. And that's it. Can is there any other is there anything else? Am I missing anything? Yeah, is there any other thing? A equal to 0? Yeah. If a equal to 0, then yeah, am I missing this one? So what should it be in case of 0?
I can be something as 0.
Okay. But can it be 0? Can a be 0? Ah, guys, what do you think, people? Yeah, absolutely. So a cannot be 0, right? So these are the small things. Again, this is not a mathematical point. Just have to be careful. So yeah, six-digit number, so it cannot be. So you see, for B we have 10 choices because B is not on the left, so it doesn't have a responsibility to uphold the digit number. So it is B has 10 choices. So let's summarize. Yeah. So these steps you have to just so this is a slightly interesting question. You can do this with a lot of casework also, but this is a little still this has a bit of casework. But this is just because we are new to these things. Okay, so no problem. So B has 10 choices. 10 choices for B. Okay. And then for each of these 10 choices, because as we said, B doesn't matter here, whatever B is. Okay. For each of these 10 choices, that's why I'm multiplying. We have all these choices. How many are here? Can we count it? See, we had to list something. Okay. So I said in the beginning that without actually counting, but some things you have to count. So how many are here?
A has 9 choices.
No, no, but in total for A and C, for the total combination, how many you have? Because you see, if we just say that A has 9 choices and C has 9 choices, then we can't multiply, right? Can we multiply? No, because for each of the choices of A, we don't have 9 choices for C, right? So if we just look at the total choices here in the picture, so you see there are 2 plus 2, 4, 6, 8, 9, 10, 11, 12, 13. I think I'm missing something. 2 to 4 to 6 to 8, 9, 10, 11, 12, 13. Hmm. So if A is 3, no, it should have been it should have been 14. We are missing. But in any case, if we are missing something, you guys can just figure it out. So there are 14 choices, right? So you see, we had to do an addition there, right? We had to add. What did we really do? We are just adding 2 plus 2 plus 2 plus 2 plus 1 plus 1 plus 1 plus 1 plus 1, whatever, something. Yeah, this is right. Okay, this this is the answer. Okay, because for any choice of B, we have these many ways. Right, because if you put B equal to 0, still this would work. These 13 ways would work. If you put B equal to 1, still these will work, and so on and so on. So it doesn't really matter what you put in place of B. So the answer is 130, 10 into 13. Okay. So any doubts, please think about this. If there are any questions, let it sink in. If you want to quickly take some notes, if you need to. Anyways, yeah, this is not to think about this. Maybe try it again. And maybe you guys can try it for 3. If not be trivial, just think about it. Okay. I mean, all this would take much less time if we know some more number theory. And probably you guys already know a trick that is there. You must may have read somewhere. Maybe you don't know the proof of. And there is a following. So there is a trick, right? And this is again just a number theory fact, which we in some sense have already proved. But in any case, the trick is like this, right? If you want to check the some number like this, any number, If you want to check if this is divisible by 7, so I'm just saying in words, okay. If you want to check that this whether this is divisible by 7, then all you need to do is you need to write this, then you need to write minus of the next block, and then plus of the next block, and then minus of the next block. And you want to check if this is divisible by 7. Okay, I'm not writing it in words, but maybe some of you would have seen this trick. I read it somewhere, just a fact. It's not hard to show, but we'll see this later on. That's what we used, kind of, right? If you just take blocks with alternate blocks of 3 with alternating, and this being divisible by, if this is divisible by 7, then this is divisible. So these are the same things. Okay. Think about why this is true. It's an interesting question. Okay. So yeah, let's see. So we have many questions like these which are uh, motivated by numbers. Okay, and it will, it's just a very interesting sequence chain reaction kind of, which will just, you know, push you to learn more number theory, just out of curiosity and so on, from these things. We already saw in the weights problem, in this problem, so it's a mixture. Okay. However, numbers and digits are just one aspect. Counting questions can be asked in so many contexts, right? Many contexts. Let us just see one in the context of, we'll deal with them more incisively and also more we sidewise develop the language of factorials and so on also. But let me just give one more context and then we'll end there. Okay. So counting, we want to understand in the context of points and lines. Okay. So I am teaching this, rather, just discussing this uh, topic called graph theory, which is also in the syllabus of PRMO, but I think we have kind of discussed much more than that, which, but anyways, that's not the point, where we have looked at a lot of properties of points and lines and graphs. Okay. Um, yeah, so, but it's slightly, that's has gone slightly advanced, so we'll, when we revisit it, see. Um, yeah, if you guys are interested, you can tell me. But in any case, the point is, in this context also, we can ask a lot of interesting questions. Let me just frame one. It's very simple. Just framing. Let's say you have some points. So you have this 8 points. Okay, 8 points, 8 islands, whatever you want to call it. And we want to make bridges between them. Okay, we want to basically join them. We want to join them by lines. They are also called edges. The question is, how many bridges are possible? How many bridges can we make? This can probably be done on several levels. It can be done very by starting with the case of 2 points and 3 points and 4 points and then seeing some pattern. You can do it like that also, but we will not do it like that because that will be too baby version to do. So one way is patterns, seeing pattern. One way is to see patterns. So when there are 2 points and the answer is one, when there are 3 points and there are three bridges, when you have 4 points, you can just check that there will be six bridges. You can kind of see some pattern. Next time there will be 10 bridges. I'm just rushing this a little bit, but you guys can see the pattern. And then what is the pattern in these numbers? So this is maybe one homework which you guys can try, right? Just take the small cases and count them explicitly, like actually count them and see the pattern in these numbers and try to guess what will be the eighth one or maybe the 18th one or the 80th one. Just make a formula. Try. It can be done very elementarily. But if we just want to not do that, that's there, but we want to just do it in a slightly more. So this is something that you should, guys should just try. Okay, let's try it with patterns. What could be a more interesting way to do it? I mean, choices and so on. How many choices does each point have, or something like that? Okay, that's what we want to think about. So how else can we attack this question? We want to understand the number of bridges. How many different bridges can we make? And later on, we'll answer for triangles and also other very interesting things. Okay, this is one bridge, this is one bridge, so on. Many bridges are there. From what perspective should we think?
Like how many options our theory point have out of those bridges.
That's good. Yeah, that's what we should do. So let's name these points. And also, you would notice one thing is to digress a little bit is that the position of the points is not very important. That's why it's a combinatorics question, not a geometry question. Okay. So 1, 2, 3, 4, 5, 6, 7, 8. There were 9 points. No, this is just yes. So basically, we have to think from the perspective of the points, right? Yeah. How many choices does each point have? Does each point have? Or how many lines can be drawn from every point? How many neighbors does every point have? So what should be the answer to that question? 7, right? Because there are 7 options. So each has a 7. So this has 7. So each of them have 7. So what should be the answer? 42. Why 42? So out of each there are 7 things coming.
56.
56. 56 at the first look, that's, but think little more carefully. Okay, so each of them have 7 choices and there are 8 of them. So there are,
One is the combination of them. If we are, if we use your 8 point of view, still we need to bridge with 7 again. If we choose 7, still we need to bridge with 8.
that's right. These are the things you have to be careful about. Yeah, so that's the point, that every bridge, so the answer should be 7 into 8, but you have to divide by 2, right? The reason is, and as you already said, that each bridge, in the way we are doing, in the way we are proceeding with this question, each bridge is counted twice, and exactly twice. That is the good thing. So in this case, you see, there is a strategic overcounting. There is an overcounting, but we know what we are doing. Huh? That is really the thing. Sometimes we should not be afraid to just do it, and then later on we can divide. Okay. So each bridge is counted twice, exactly twice. Okay, when you visit the point 8 said, so because each bridge has 2 points, 2 endpoints, and it will be counted twice, so we should divide by 2, right? Because counting everything 2 times. So that's it. The answer is this. So in general, the answer would be n into n minus 1 by 2. So this is what you get when you think from the perspective of points. Okay, but it turns out there are more advanced methods suggests which can be generalized later on to triangles and so on. Okay, but right now, I think it's better to not say. This is just an explore. So I will send some regular questions because this is, I'm trying to make this a little more, a little regular class, at least in the first two, because it's such a foundational topic and it needs some language and some theory. Like for the grass class and so on, we don't really need that. But here we need some. So that's why I'll just keep it formal for a few classes. Then we'll branch out and so on into more. So I will give some basic questions, routine questions to try. But right now, this is just a fun question that you guys can try. How many triangles are there? So this is not trivial. Okay, how many triangles? So like this, huh? One particular triangle, like 168. How many different triangles can we make? Think about it. Okay, so think about it, and then so that's it for today. In case otherwise, if there are any questions, you guys can tell, ask.